So previously, we've talked about the discovery of light and gravitational waves from the collision of two neutron stars, something that people have called a kilonova, and how thousands of astronomers around the world observed that event in all different kinds of ways, in different wavelengths and in the gravitational waves.
But this was something that people had predicted years before, and found that the observations of the one kilonova that's ever been seen actually looked pretty much like what they said it would.
Yeah, and we actually have one of these astrophysics prognosticators on the show today. Professor Brian Metzger from Columbia University, one of my old friends from Berkeley, is here with us, and was somebody who had written down some predictions about kilonova before we found the first one. So, what predictions had you made, and sort of how did you come up with those before we'd ever seen one of these things?
Well, I think the main thing that we contributed was the first predictions for exactly how bright these things would be. And the reason they're called kilonova is because they're about 1,000 times brighter than normal nova, classical nova that happen in our galaxy. And so by figuring out the nuclear physics that tells us how bright they should be, we're able to kind of give them a name, that's commensurate to how bright they are.
So, how do you go about coming up with predictions for what this is going to look like before anyone had ever actually seen one?
So it's interesting. I mean, the idea had been around for about a decade that if you eject neutron-rich, neutron star guts into space, that you'll create heavy elements. But no one had actually tried to calculate what heavy elements are produced and what their decay properties were. And so at some point, sitting in my graduate office, probably right next to Jeff's office at Berkeley, I realized that we had to get a hold of some nuclear physicists. And so I contacted a few people I trusted, and they put me in touch with the people that could do this calculation, or I could work with to do this calculation. And so it really was, an astrophysicist realizing he needed help from nuclear physicists and making that connection.
Yeah, that's something that I feel rarely happens, science crossing these sort of department or topic boundaries. But it seemed to work out really well. You got a lot of the predictions matched a lot of the observations, but what was surprising? What was either different or shocking about once this was found and all these papers came out with thousands of astronomers, what we actually saw in space versus what some of your work had predicted?
I think the early phases of the kilonova, we had predicted they could be blue, but I think that how bright they was a little bit brighter than we thought. So a little bit, I don't want to say too blue, but it's a little bit more luminous than we would expected. And so that means that there was a lot of radioactive material that was ejected from this merger, maybe more than what some of the simple models would have predicted. But that's great because it also means that these can be a really important source of these elements in our universe, right? So the fact that we saw one, even though we saw just one merger, it produced so much material that a large fraction of the, gold on my wedding band could be arising from one of these mergers.
So now that we've actually seen a kilonova out there in real life, where will our theoretical understanding of these events go from here? Have you developed your models based on the observations that have actually been seen?
Yeah, I think the exciting thing is that with the LIGO interferometers and the Virgo interferometer, being upgraded right now, whereas we had one event discovered during their last observing run, we can hope to detect several of these, and possibly once they reach their design sensitivity, once every month. And so we're going to see different mergers, with different masses of the ingoing neutron stars. We're going to see the same types of systems from different viewing angles, and we think that the ejecta is very aspherical, and so it's going to look different if we're viewing it in the equatorial plane versus if we're viewing it down the rotation axis of the binary. So for this particular event, we think we're about 20 degrees off of the rotation axis, but maybe the next one will be 50 degrees and it will look completely different. So I think that's what we're getting at right now is to try to map out the diversity of outcomes of mergers and how it is going to translate into what we see. And that's going to be the real test of if our models can hold up, right?
Yeah, you got one right. Let's see how many more you can get right with some of your modeling. That's cool.
Well, let's see. Right. Yes. Nature, I'm sure, has more surprises in store.
So we've been hearing a lot about how all of the heavy elements, so you mentioned like the gold on your wedding band, come from merging neutron stars. This had been theorized for a while, and now we've actually seen one, so it seems likely to be true. But how does that actually happen in practice?
when you eject material, it's extremely hot, so you just have free neutrons and protons. It's a lot like the Big Bang. But as it expands into space, it cools, and what happens is very quickly, all of the protons and some of the neutrons get together and create these heavy seed nuclei, which are about as heavy as iron. But you can't form through standard nuclear processes. You can't form much heavier elements. But then you have so many neutrons left over that they then bombard these nuclei and build up these really heavy radioactive ones through neutron captures. And it takes about a second. It actually takes a while. So the matter is ejected within a few milliseconds, but it actually takes about a second for all the nuclei to be created. And once they're created, then they just decay back to stable ones, over a range of timescales.
I love that you say it takes a second, and that's a long time.
Well, second is a long time in the scheme of things. Yeah.
But in overall, if you're trying to build up elements, it's pretty rapid, you might say.
Yeah, sorry, I didn't say that. Yeah, so it's called the R process because it's the rate of neutron captures is very rapid compared to the rate at which they decay.
Another very creative astronomy name for a technical process.
Yeah. I mean, the first heavy elements that were ever seen were, of course, technetium seen on very massive stars, and those are produced through the S process, which is a process where you create heavy nuclei by slowly capturing neutrons. But it's been known since this famous paper in the 1950s by the Burbages and Hoyle and Fowler. It's been known that you can't make all the elements through the S process. You need an additional site in nature where the rapid R process happens, or the rapid process happens. And we finally found one site. I should say that I don't actually think it's the only site. I think there are other sites in nature which can do this, but this is the most conspicuous. It's interesting. The other thing I should say is just how things have evolved. When I started in this field, when I was a graduate student at Berkeley, you could open your textbook and it would say the R process happened in supernova. And there was a review article that was written on the topic, and probably shouldn't publish this because the person who wrote this review article is probably listening. But there was a review article on the R process. It was called "Where Has the R Process Gone?" And the neutron star mergers got a footnote on the first page that said it's well known that they don't work, basically. And now I'm going to talk about all the ways that supernova don't work and why I'm so confused. And so it's amazing just in a decade how we've gone from not knowing anything to knowing quite a bit. But have we swung too far? Have we said now everything's mergers and not been as creative as we could be about other places in nature that could do the same thing?
So yeah, going from we think these heavy elements come from this other system. We don't know what neutron stars are doing when they crash into each other. We've never seen that happen before, all the way to we've seen a couple crash into each other. We've seen the heavy elements come out of it. That's a pretty big paradigm shift of where does gold and platinum and silver come from?
No, it's really incredible. And hopefully our understanding will keep evolving. We're going to see more of these. We're going to see the diversity of their riches.
Well, thank you very much, Brian. Great chatting with you. Cheers.
Cheers.
Cheers.